Today I am presenting a working paper from our university, and it is about the application of machine learning approach in the prediction of carbon emission at firm level. This paper is written together with two of my supervisors, that is Associate Professor Diaz-Rainey and Dr. Duminda Kuruppuarachchi. And we welcome all kinds of comments in order for us to improve the paper. So before I start, I would like to provide a little bit overview about the motivation and the story behind this paper. So as the name already says, we only have one research question, and that research question is about whether we can predict carbon emission at firm level using externally available data. And so if the answer for that question is yes, so we want to understand what is the prediction accuracy and what can we do to improve the prediction accuracy. So that is the underlying research thesis of our paper. So now, I'm sure that everyone in here already know about carbon emission already, and in, the prior paper already mentioned about scope 1 and scope 2 emission, but just to provide you a little bit definition about that. Scope 1 emission is the emission that come from the direct emission that come from the production process. Scope 2 emission is the emission that come from the purchase energy, and then there is also another scope of emission that is we call scope 3 emission, and it covers the upstream and downstream supply chain. And then actually for scope 3 emission, there is a lot of inconsistency because the company can actually choose what kind of activity they want to involve in the calculation process. And also because of that, there is not a lot of company that disclose scope 3. And then it is also very hard for you to predict scope 3 emission. So in this paper, our focus is on scope 1 and scope 2 emission, and we also try to aggregate data together and to see if we can actually predict scope 1 and scope 2 emission separately, or we can aggregate it together and have a better prediction. So that is the baseline of our paper. Currently, most of the traditional process in calculating carbon emission at firm level, they are using input-output analysis or process analysis, or a hybrid approach, and then most of the calculation process, it requires very extensive data collection effort. And so because of that, I don't think that there is a lot of firms that are disclosing carbon emission as of this moment. So moving to the motivation why we have this paper, actually it comes from two facts. The first one is because we have a rising interest in terms of using carbon emission as a process for climate transition risk at firm level. So what we have is that we have a lot of low carbon index developed by S&P and also developed by MSCI. On the other hand, we also have commitment from institutional investor to a low carbon investment strategy, and we also we have the UNPI signatory. And then last but not least, we also have the carbon stress testing that is currently proposed by McCartney for the Bank of England and for the other bank in Europe. And this kind of stress testing requires a level of data aggregation from, let's say, from firm level. And then with the fact that we have very low disclosure, it is actually very hard for you to proceed for climate transition risk, especially if you are looking at, a portfolio with small scale firm or the portfolio international firm. So it is much harder for you to look at it like that. Then moving to the degree of disclosure, we have the CDP project, which is covering the volunteer disclosure, and there is only around a couple of thousand firms that is actually disclosing scope 1 and scope 2 together. And then meanwhile, if we compare with the number of companies out there, in another project, we look at all firms in the world, and we download the data from OBIS. There is actually 190 million record of firms. So just to compare, that is how small the volunteer disclosure are actually happening compared to the list of firms. So that is where we think that we need to have prediction in here to somewhat fill the gap and to spot the analysis of climate transition risk, especially in the context of finance. So with that, what we did is that we scanned through the literature And it is no surprising. We actually find a very few literature in terms of like prediction of carbon emission at firm level. There is actually two strengths of literature. One comes from the commercial data provider like MSCI or Thomson Reuters Access 4 or CDP project. And then another one, it comes from the financial researcher that is the Griffin et al. And Gohammer et al. And all of these papers are published in finance and economic paper. So what they find out is that actually it is possible for you to explain carbon emission using externally available data with the adjusted R-square for the example adjusted R-square that can reach to like 70% to 80%. But then the other thing that we noticed from this paper is that most of these papers, they are implementing kind of a naive approach, a very simple statistical approach. And then with that, we think that there is room for improvement, especially with machine learning approach. I'm going to go through the reason why we need the machine learning approach in here. We think that like with the traditional financial analysis, especially with the traditional academic research, one of the most important things that people care about is about causality, whether X generate a change in Y or not. But then for prediction, the problem is not about causality, the problem is about correlation. And then sometimes in order for us to have a good prediction, sometimes we sacrifice theoretical accuracy to have better prediction. So like the problem with the OLS regression is that it tries to find an unbiased estimation, but then sometimes we can actually trade off a little bit bias to get like a smaller variance. And then when we look at the prediction error, it is a composition of bias, variance, and noise. We can actually reduce the prediction error by creating a bias estimation. So that is the whole concept behind machine learning approach. What we did is that we try to have a trade-off between bias and variance, and also with that we also can conduct the trade-off between cost and complexity. So which means that we can create a model that is complicated enough and it can predict out of sample good enough. So that is the whole scope, whole intention of machine learning approach. Today what I am presenting is actually a very basic machine learning approach that actually anyone who have access to like Python or scikit-learn can actually implement that. The model that we are using is a meta model that combines the prediction from the base learner, and it will try to learn what is the best way that could be assigned to each of the base learner, and then combine together to have the best prediction. And then the base model that we are using here is the very basic one from every machine learning paper, and that includes the linear regression, that is OLS, and is counting like elastic net. Then we also have like non-parametric model like k-nearest neighbor. We have non-linearity model like neural net. We also have tried like ensemble of decision tree, and that should be random forest and gradient boosting. And then that is the base model that we are looking at. The reason why we look at combination of model is because it has been used extensively in the prediction literature, and it has always been kind of like always is the winner among the cargo competition in terms of what is the best model for prediction. What we did is we used the data from 2005 to 2017. We have around like 14,000 firm year observation. We require that all the firms have to disclose scope 1 and scope 2 separately. And then with that, we divide that into tenfold for cross-validation. And I'm going to talk about it later, but our measurement is not about in-sample goodness of fit. Our measurement is about out-sample mean absolute error. And what we want to do is that we want to reduce the mean absolute error as much as possible. We also conduct a lot of robustness tests, and I'm going to walk through that into more detail into the next session. Then our finding is like consistently to the prior finding, we find that it is actually possible to explain the carbon emission variation among a universal group of firms. And in here we also have the adjusted R-square, but then this adjusted R-square is out of sample adjusted R-square that can reach to as high as 80%. And we see that if we applied an optimal set of predictor, if we apply, a variety algorithm of machine learning algorithm, and if we try to combine models together, actually we can see the improvement in prediction accuracy, and it can be as few as like 25% to 30% compared to the baseline model. However, what we have to say is that even though we try to reduce the mean absolute error, this is the log transform mean absolute error, is still as huge as 0.696% in terms of log transform MAE. And so with that, actually only around like 52% of our sample is predicted within a certain range. And so with that, we say that even though it is possible for us to predict like carbon emission at firm level using universal data, it is actually doing not very well in terms of like predicting absolute value. It is better in ranking, and I'm going to show you later, but it is not good at like calculating absolute value. And then what we find is that if we introduce the direct predictor, like energy data, like energy consumption, energy production by fuel type, actually it can generate a very huge improvement in MAE. And so with that, I'm going to go through into the research methodology. So for those of you who are not very familiar with machine learning, in machine learning we have a concept called like cross-validation. And so often what we did is that we divide our data set into like a number of folds. We change the data on like k minus 1 fold, and then we test the data in like the other fold. And that is what we call cross-validation. In our paper, because we also employ meta model, so actually we are having like two layer of cross-validation in here. We go through a process for us to evaluate, to train model, and to test the model. Our data come from like Access4, from Aiken, from IEA, and from World Bank. We need to go through like some pre-processing data first, like how to deal with missing value, because a lot of firms, while they have like revenue data or access data, they don't have like information. Some of the case they don't have information, like they don't have intangible access or stuff like that. So one of the decisions that we need to make is that how should we deal with missing value and how should we deal with outlier. We continue with the prediction of using the base learner, and then we combine the base learner together in another layer called the meta model. And then with that, we finally evaluate with out of sample MAE, but we also look at like the R-square and also another kind of like robustness test to ensure that our prediction is actually reliable and robust. So in the very first step, what we did is that we carry out a very simple linear regression. And we want to see what kind of like predictor we should put into our model. So in order for us to do that, what we did is that we assume that carbon emission is actually a side product of the revenue generation process. And so because of that, it is actually a function of scales of operation, of business model, of technology, energy, and also environment. So this is the first step that we did. We have actually a lot of like candidates for our predictor. Like in terms of scale, normally people will use revenue, number of employees. We also think that probably we should factor in the growth. We should factor in the equipment, and we should also factor in the total access. We should also factor in leverage, and so that is the scale of operation. So in terms of business model, one of the very simple processes that we look at the gross margin. We think that if the firm is in the upper level of the global supply chain, it should have like high gross margin, and it should use like low material and low energy. We also like try like different type of industry classification. Normally in the other model they use like GICS classification. We have actually many level of GICS classification like sector, industry group, or group. So we want to find out what should be like the right level of classification that we should use here. And we also try like the other classification, and we try to also reclassify by ourselves based on the greenhouse gas accounting methodology to see if we can actually improve the prediction accuracy. We add in, because our model is looking at the entire global firm, we also want to factor in the environment that the company is working on. So we are assuming that if they are working, they are operating in a environment where there is carbon law or there is carbon pricing, probably they will try to make decisions to reduce the carbon emission, like the other paper that they just talked about. And then also, like, we also include like energy factor, and in energy factor, one of the most important factor that we include, that is the carbon intensity of national fuel mix. And then we also like try to see if we add in like production of energy and consumption of energy, that is like semi-available predictor, will that improve the prediction accuracy or not? So that is the first step in our calculation method. With the optimal set of predictor in the first step, what we did is that we carry on with the base model. We are using like 6 model in here. One is like OLS and elastic net, two nonlinear model that is k-nearest neighbor, and neural net, and also 2 ensemble of decision tree, that is random forest and gradient boosting, actually XGBoost. Most of the model, the most important concept of machine learning approach is that we need to do a trade-off between cost and complexity. So which means that we can create a very complex model that can actually predict every single observation of the ensample correctly. Like you can build a very big tree and have like a lot of branch that can, and then each of the branch, it can point to one observation. But then with that, it is going to like create a very poor out of sample prediction accuracy. So for all of the model, we have to like set up the parameter so that we can conduct the trade-off between cost and complexity. So I'm not going to go through detail like what kind of like parameter that we need to use, but basically some model they use very simple parameter, some other model it is a combination of multiple parameters. And what we need to do is that we have to do like sequential grid search, or like we do random search or Bayesian search to get the optimal set of hyperparameter. And this is the model that we use. So so I'm going to walk through. For the meta model, what we did is that we try to combine the base learner by using another trainable model. So normally when you have like a lot of like base learner prediction, you can actually just like average it out. And most of the time when you average it out, it actually can improve your prediction accuracy. But then sometimes you can also change the model. You can say that I want you to learn inside the model itself, like what is the grade that you should dedicate to like XGBoost, what is the weight that you should put to the linear model, and then with that you can even have a better accuracy. So I'm going to go through quickly into the result. The first step is like selecting the optimal set of predictor. We find that on the left hand side, that is the MAE of the Gohammer model and the Griffin model, that is our base model. And then with that, we go through like different decisions, and then we find out if we change like industry classification from sector level to group level, it can improve the prediction accuracy. If we add in a lot of predictor, if we combine predictor together, it can also actually improve the prediction accuracy. You can see that that is the improvement for each of the model compared to the prior model. So every time it just like create only like 5% or 6% improvement in prediction accuracy. But then when it combined together, it is actually a good improvement. It is around like 15% or something in here. Then with the base model, what we see is that if we carefully tune the hyperparameter, actually it can also reduce the prediction error. And the best model in here is the example decision tree. That is random forest and archivals. Both of them can reduce the prediction accuracy, improve the prediction accuracy like by 12% or 10% for each of the scope. We also have similar result for the meta model. Actually, for meta model, it takes a lot of our time for us to like tune the model because it includes a lot of like stacking generation. But then our improvement is quite small. It is around like 4% compared to the best model from the base learner. That is the random forest. However, this 4% actually it has been tested, and it is actually a real improvement in our Wisconsin side rank test. So like in total, we have like 25 to 30% improvement in prediction accuracy. And here's the box plot of the mean percentage absolute error. And we see that with that one is OLS, and we see that the application of base learner and meta learner reduce the size of the box, but then also at the same time, it reduced the bias in the model. So in the OLS regression, the average MAPI is around like -1%, but using meta-elastic net, it can actually reduce it to like 0%. So that is one thing that we think that our machine learning framework also works. Yeah, so I'm going to skip through this one, and we have a lot of robustness tests, but one key important thing is that with our robustness test, we figure out that our model is actually performed very well in terms of ranking, which firm is bad at emission and this firm is good at emission. It can achieve the accuracy like up to like 86%. And with that, we come to the conclusion that we can actually improve the prediction accuracy using machine learning framework in the regression problem. But then in order for us to achieve better accuracy, we need to like take more time in terms of like the predictor. We need to like properly collect predictor in terms of energy, consumption, and production to achieve a better improvement. And that concludes our paper.